sure we have to look to thanks to Dr. Lisenfeld for being here today to talk about tunable systems and decoherence.
Thank you. Yeah, hello, and welcome to the second lecture about tunable system defects in superconducting quantum circuits like qubits and resonators. So, okay, let me just start here actually. Yeah, so last lecture we had heard about superconducting resonators, what we can do there to study TLS, and also how TLS defects they generate noise and decoherence. And today I'm going to talk about superconducting quantum bits. Before I start, do you have any kind of question about the last lecture, any feedback, any complaints? Okay. So better. Yeah, okay, so in this lecture I'm going to briefly give an introduction to superconducting quantum bits, a very brief one, and of course talk about decoherence, which is the kind of Achilles heel of the superconducting quantum bits, so the weak point. And then of course also bring you to the state of the art, and later we will talk about the decoherence in more detail, what is the origins and what we can learn about that, and maybe how we can even mitigate it. So, very brief introduction to quantum computers. I mean, I probably guess we all know that quantum computers would be very useful if you would have one. We could be able to do simulations that we are not able to do now with classical computers. And the interesting questions are just like this protein folding, where you try to understand how the RNA is actually translated into the proteins. This goes a very difficult path of like this folding, which contains various quantum effects that evolve in time, and there's many different paths. So it's a very difficult problem to try to simulate this with a classical computer. That's why we would like to have a more powerful computer. If you would have that, we could actually use this to not only develop new medication, also we could use it to make really designer proteins. I mean, yeah, exploit this nano machine basically to generate everything what you want. And yeah, of course also heal through sicknesses. Another good use of a quantum computer would be actually rather well, trivial one if you wish, but it's not so trivial. This is about catalysts. So if you want to make a chemical process efficient, like for example the generation of ammonia, then typically you need some catalyst which just promotes this reaction. And finding such a catalyst is actually a very difficult problem. Again, of course, you have to deal with quantum effects when the molecules here touch the surface. And a very good use for that would actually be to generate this ammonia, because it's not only the basis of explosives, but also of course of fertilizer. So, which is of course feeding the world. So, having a more efficient process here than this rather old catalyst, which just was discovered more or less accidentally, more than 100 years ago, could efficiently help us to save energy. And in fact, this ammonia synthesis already takes like 1 to 2% of the world energy consumption, energy production. So you could save a lot of energy here if you would be able to do this more efficiently. There's other uses, of course. I mean, you can do optimization problems more efficiently. For example, to make a computer chip route the wires more efficiently, or just find a better way how to travel through a country. And also we could use a quantum computer to explore physics, which you cannot just reach technically. So at some point we may not need to build anymore these larger particle colliders, for example. You could just try to simulate this with a desktop quantum computer. Yeah, there's a lot of hype, of course, about these quantum computers. I guess you have heard about it, especially in the last years. There were many headlines. This was around the time when also commercial companies started to delve into the field. So companies like Google and IBM jumped into that, and now also have very strong effort in research and development to build such a device. And you can imagine that this gives a lot of large push to the field, simply because these companies basically have unlimited funds. So yeah, to finish this very brief introduction, just have to understand, to build a quantum computer, we need, first of all, quantum bits, which are just quantum systems having two states, 0 and 1. And of course, the key point about quantum mechanics is that you can have this quantum bit also in a superposition, like two states more or less simultaneously. And now if you build a quantum memory, so just a large set of quantum bits, then also you can put this into a superposition, and already like 270 quantum bits would have 202 to the power of 270 different states, because the kind of memory capacity scales exponentially with the number of qubits. So if you want to double the memory of your quantum computer, you can just add a single quantum bit. And of course, like just computer, you would have to put another same size memory chip inside. So this exponential scaling is the basis of this power which quantum computers have. And moreover, once you have such a quantum memory, then you can convert it in a superposition, which means that you can store, basically all these many states at the same time in this quantum memory. And if you would then have a quantum computer, the quantum computer would just accept this superposition of information as an input, digest it, do the calculation in parallel on all these different input states. And at the end, then you just get a superposition of all the outcomes, all the results for each individual number in the superposition. And this is called quantum parallelism, actually the basis of why quantum computers can be so powerful and why their power scales exponentially in the number of qubits that we have. So last lecture we heard about superconducting resonators. And of course, we heard this is already a quantum system, so we have discrete states here. We could in principle think that we can just use two of these states as the basis states for our quantum bit, 0 and 1. But it's actually not possible because it's not possible to just prepare one of these individual states without any nonlinear system. So if you, for example, just start to drive such a resonator with a resonant field, you don't only go to the first excited state, but rather you generate a superposition of excited states, so-called coherent state or cloud resonant. So it's a quantum system, but not useful for quantum computers. We need some nonlinearity. And luckily, there is a nonlinear element that we can use, which is the Torsson junction.
Sorry, once again, why do we need nonlinearity?
Yes. Okay, the principle is very simple. If you drive the system and you want to pull, for example, from the ground, set at the excited state, you apply some asymmetric field with a photon energy just similar to this energy difference. Then you can absorb this photon and go one state up. But you see, the energy difference between the neighboring states is all equal. So if you start to populate the excited state, the same Barry field will just then transfer this excited state to the second excited state. And then it goes up, then it climbs up the ladder. And that's why you get this Poissonian distribution of the level population.
So you just need non-linearity to make the energy difference between.
This is the one.
Okay.
Yeah, exactly.
In this specific configuration.
Well, you need some potential which is not harmonic.
Yeah. Okay. Oh, okay. Yeah.
Yeah, and then you may have unique transition frequencies between the states.
Okay.
Yeah. So this nonlinear element is basically the Torsson junction, and I think that Sergei Frolov already explained a lot about these junctions, so I can also make this brief. You have just, the junction is just made by two superconducting electrodes, which are separated by a thin dielectric tunnel barrier. So this is a light insulating barrier, and then basically you have the wave function describing the superconducting state in both of these superconducting electrodes, and the degree of freedom this junction has is only the phase difference between these two superconductors. So this is the degree of freedom that we have in the Torsson junction, basically the difference between the phases of these wave functions. So this junction is characterized by some maximal tunnel current, so there's a maximum current which can just tunnel through the junction without dissipation. And obviously this looks like a capacitor, like a plate capacitor, so also we have some capacitance in the system. Yeah, the total equations, I guess you all know them already, are given here. So the current basically depends as a sinusoidal function on this phase difference. And if you have some phase which changes in time, you will see that there will be a voltage drop across the junction. So this is basically the results Brian Josepson had when he was a PhD student in Oxford, and for which he also got the Nobel Prize. Yeah, now to come back to nonlinearity, thinking about electrical circuits, you can now think about some nonlinear inductance. So you can actually just use the definition of the inductance So if you have some inductor and you actually try to apply some current through it, the inductor will respond with a negative voltage trying to expel this current. So at the end, using these Torsen equations now into this definition of the inductance, you get here some equation for the Torsen inductance, which you see here depends also non-linearly on the current. So this depends on the 1 over cosine of the phi, and this is just this function here of the current. So you have your inductance, which just changes depending on the current which you put through. This is obviously not a linear device, but just this nonlinear device that we will need. Okay, the energy scales which we have to consider later are these two. So we have the energy in the tunneling current, or the Torsen energy here, proportional to the maximum tunnel current, and we have some charging energy, which is just the typical charging energy of the capacitor. Yeah.
What is the right sign in front of the inductance?
Well, yeah, this is a bit of the definition. So the idea is that if you have an inductor and you try to put some current through it, the inductor will induce a voltage which actually tries to block this current, to keep it out. So it's like opposing this current flow. But actually, I have also seen definitions which don't use this sign, this minus sign. So at this point, I guess it doesn't really matter whether we have plus or minus here. Okay. Yeah. Okay. Now we can come back to our problem in the beginning. So we want to build some superconducting circuit with some nonlinearity. So why not just use the LC resonator, now replacing this linear inductor with the Torsen junction, this nonlinear inductance. And if you do this, you can, for example, have a potential energy which is now not anymore harmonic, but has just this cosine phi, which is given here in the Hamiltonian. So this is basically just a Torsen energy depending on the phase difference across the junction. This is just the charging energy. Yeah, now you can see that you have what you need. You have now unique transition frequencies between the states. You have a higher energy for the first state and a bit smaller energy you need for the second state, and so on and so forth. Yeah, and this means now we can actually isolate two states only between which you can operate, and then use this as a quantum bit. So brief words about how we make these superconducting Torsen junctions. Typically, we use, of course, nanolithography in a Dolan bridge configuration. So this means that we make some double layer of photoresist, which is shown here in the cross section. And the idea of this double layer of resist is that this lower layer here is a bit more, well, responsible to the light by which we expose this field. So basically, we need less energy here to expose the lower layer and higher energy to expose the upper layer. And this means that by just changing the dosage which you use in different places, you can generate such undercuts here and also these free-hanging bridges. And especially this undercut is useful if you want to make a coherent quantum bit, because if you wouldn't use this undercut, you will get an effect which is shown here. So at the end, to make the junction, you will evaporate metallic layers on this structure here, as you will see in a minute. And if you don't have this undercut, this metal which you evaporate there will also just be deposited on the edges of this photoresist. So if you then remove the photoresist, it could happen that this metal on these edges of the resist actually remains and builds such fences here. So like sharp, upright metal things here. And these are a problem for decoherence, as you will also understand, I guess, in the rest of this lecture. So now to make the junction, actually, you use such a Dolan bridge. So this is now the cross section along this line, and then you will start to evaporate. So you can use aluminium, for example, as a superconducting material, which is actually the one by which still today nearly all Torsen junctions are made from. And what you do is you first evaporate aluminium under a certain angle. So it's not directly straight. And then you can see that this Dolan bridge here casts a shadow here. So you have then basically this red bottom electrode, which is interrupted by this position here. Now now you can grow the tunnel barrier in a rather simple way. You just let a bit of oxygen to your vacuum chamber. Then, of course, the aluminum oxide will just natively grow and form here a very thin tunnel barrier, which is typically about 2 nanometer thick. And the next step, then you is the top electrode, and now you again evaporate aluminium, but from a different angle. And again, you can see that this Dolan bridge here casts a shadow, but here you have the overlap between the superconductor, the insulator, and the superconductor, which forms the heterosis internal junction. This is in principle already all you need to make the junction, but in principle, one technical problem which typically appears here, which will also reach us again later when you think about decoherence, is that this process not only makes this wanted junction here below the Dolan bridge, but there's typically also another junction made here. Because, well, obviously when you want to contact the second electrode, everything here on the chip will already be oxidized. So everything will be covered by this tunnel barrier, and this means that it's very difficult actually to make only a single junction. Typically you make also so-called straight junctions or parasitic junctions. So the nice thing is that this tunnel barrier, this junction area, just depends then on your resist thickness, which you can of course nicely control just by controlling the rotation speed of your photoresist spinner. And also by changing the angle, you can achieve very small dimensions here. So typically we need to make very small junctions for coherent qubits, which are typically maybe 200 by 200 nanometers large. Okay, so now let's just jump directly to the transform qubits, to the quantum bits which we use nowadays.
Sorry, but what to do with the problem which you mentioned, this some additional junction?
Yes, you will see later why this additional junction will make a problem. Yes. Okay, so today the way to try to build a quantum computer really only uses so-called transform qubits. I mean, there's different types of qubits, but I don't want to go into all of them. So this is definitely the one which we have the highest hope at the moment. So again, it's just some twisting junction and some capacitor. Then we get this cosine potential that we need to make this quantum bit. And the idea of this transform qubit then is that it's actually an advantage if you make this capacitor relatively large. The reason is simply that by making this capacitance large, you basically reduce this charging energy here. Meaning that this is something which protects you from charge noise. So charge noise is just in solid-state physics and really everywhere the major reason for noise and also decoherence, of course. And this is actually why we have to fight it. And just by putting a large capacitor here, we can make the effect of a single charge on the capacitor smaller. You can imagine if you have a large capacitor, it doesn't matter so much whether you have 1 or 2 or 3 charges in the capacitor, the voltage will be more or less the same. And that's why this capacitor actually can protect you from these charge fluctuations. This is an example of superconducting quantum bits. Now, this first one here is an older version, which actually is not a transform qubit, but a charge qubit. In principle, it's the same, so you basically some capacitor and some junction here. But here you see there's not much capacitance between these two electrodes here. And if you make such a quantum bit, you will see that the coherence time is maybe about 1 microsecond. But if you make this capacitor much larger, as we do nowadays in the so-called transform approach, we just make this capacitor much larger, and then you can directly achieve much higher coherence times. State of the art is a few hundred microseconds this time. This is just the energy potential for these different qubits. Here you see the situation for the charge qubit, and you have actually still, if you have a small capacitance, this is for the small capacitance, for this charge qubit. And here you see you have still a very large contribution of this harmonic part from the charging energy. So by just increasing the charging energy, actually changing this ratio between these two energy scales here and making this the dominant energy scale, you can see then that you have now not anymore this dependence on the charge on the capacitor. You will also have reduced the harmonicity, so basically these two transition frequencies here now are more harmonic already, so they are approaching more the harmonic oscillator, but still there is still some harmonicity because you see this second excited state is a slightly smaller transition energy than this first one. And this was actually a big breakthrough. This publication by Jens Koch, which actually contains all these basic principles of the transmon qubit, because yeah, this was the first time that you could really find a good way how to fight this charge noise.
Do you know how much we could read attention to reach the 125 capacitance?
I'm sorry, I didn't get it.
Do you know how much the size of potential to reach these high capacitance? 125.
The junction still is actually a small junction, and it should be a small junction as you will understand later. But you just have the capacitance between these two plates here. It's like a capacitor, you make it not an overlap capacitor, you just make the electrodes next to each other, because of course you have a thin film circuit, so everything has to be on chip, you cannot really go into the third dimension, so that's why this actually makes a capacitor.
Yeah, I know, but how much size of the junction?
Well, these junctions, the size of these junctions there?
Yeah. I
So typically you use always the smallest junction which you can make, typically 200 by 200 nanometers is the state of the art. I mean,
are you aluminum size aluminum junctions?
yes. All of these qubits will use aluminum oxide, aluminum junctions, yes.
Yeah, but this for me 125 is way too good. I don't know how you could this
So actually, you cannot really see the junction here. If you would like to see the junction, you would need to zoom a lot inside this. This is just the wires basically connecting this two electrodes. Okay, maybe you can clear this also later. Okay, so once you have now this qubit, this transmon qubit, you need to read out read out the state of the qubit. And here, a very good approach is to couple this quantum bit to a superconducting resonator. So we have already learned in the last lecture what these structures are. These are just transmission line resonators whose length is like, it defines the resonance frequency. You couple such a resonator simply by putting one of these open ends where the voltage has a maximum. You bring it just in the vicinity of one of these capacitive electrodes. So there's a small capacitor between these electrodes, meaning that you have a capacitive coupling between this transmon qubit to the superconducting resonator. Yeah, and superconducting resonators, you also heard, you can just read out by putting them close to a transmission line, using some capacitive or inductive coupling here, and then send a signal here and measure it on the other side. Then basically you can just use a so-called network analyzer, which will generate pictures like this. So the network analyzer just changes the frequency, which you send on one side, then you see, and you basically see how much comes back. And at resonance, typically you get a minimum transmission because the energy you apply here will be stored on the resonator, and you get a minimum on your measurement part. And this means now that you get this Lorentzian dip here in the frequency space, telling you that the resonator has this frequency here. And now, since this resonator is coupled to this transmon qubit, the resonance frequency of the resonator actually depends on the state of the qubit. So this is a sketch showing that if you have the qubit in the ground state, you could have the resonance frequency here, and if you then get able to excite the qubit, the resonance frequency would shift. This shift depends then on how much you couple the resonator to the qubit. So basically you can change this simply by making this capacitor larger or smaller. And also depends on the detuning between the qubit and the resonator. This is shown here. So this effective shift which you get then is basically called the dispersive shift. And it's also a famous thing because we have done this before also in atomic physics. One experiment was, for example, done by Serge Roche, also awarded the Nobel Prize, and he made the analog in kind of using real atoms. So his approach was to actually take some atom here, which had an optical transition. So it was possible to use light to excite this atom, also, or the atom could relax and emit this photon. And now if you put this photon here, this atom here in an optical resonator. So basically just two mirrors opposing each other, the atom inside, then this atom can actually emit this photon. It will then be part of this mode in this oscillator here, and then also the atom can reabsorb this photon. And this rate of photon exchange between the atom and the resonator is also again shown here. This is the coupling strength, G. And this is described by the famous James-Cummings Hamiltonian, shown here. Also, I promised you not to show too many equations. So, but it's a simple, it looks simpler at first point. So basically, you have here just a cavity, which is here the energy of the resonator, h omega r, with the resonance frequency of the resonator, the number of the photons in the resonator, and of course the shift for the ground state. The same you have for the qubit. You have some qubit resonance frequency, qubit energy here, and this is the state of the qubit, sigma c. So Pauli matrix can be -1 or +1. And now this coupling between the qubit and the resonator is then this part here. This is again the coupling strength. You see that you can basically excite the qubit only if you take one photon from the resonator, or vice versa. You can bring the qubit back to the ground state under emission of one photon into the resonator, here going up one state in the Fock space of the resonator. Yeah, this was one of the first approaches of this cavity QED experiments. Now actually still using these charged qubits, which have rather short coherence time. And the approach is also rather straightforward. Just again, take such a superconducting resonator here, and at a point where you have a maximum between the voltage between this inner conductor and the ground plane, you can just now place your charged qubit, and you will have some capacitive coupling here between this small island to this inner conductor, so the signal line of this resonator. And now, actually, I haven't not yet mentioned why there's not only a single junction here, but why there are two chosen junctions. Well, this is actually an advantage because if you have two chosen junctions in a superconducting loop, like here, then you can put a magnetic flux inside this loop here. This magnetic flux will induce some persistent current here, some screening current, which will just go on forever, flowing in such a circle. And this means it will also flow with different signs through the two junctions here. After some simple calculations, then you will see that you can treat such a DC split as like a conventional small junction, but you can then change the critical current of this junction just by changing the flux in this junction. So the DC split is like a tunable junction. You can tune it by some magnetic flux. This is of course very useful. If you tune the critical current, you can tune the resonance frequency of the qubit, which gives a nice way to basically adjust the qubit to a resonance where we want to have it. This is just an example of a measurement. This is now spectroscopy. So you change the frequency, which you, for example, send at one point and receive at the other. The transmission here is color-coded. And the resonator itself would have now just a fixed resonance frequency around 6 gigahertz here. And then you can change either the flux or the gate charge on this island by just putting some DC component here on this resonator. Then you can tune the qubit actually through resonance with the resonator. And you know, whenever you have two coupled quantum systems at resonance at the same energy, they will generate or show up these avoided level crossings, meaning that you have basically a position where both systems are entangled. They can share a single excitation, and basically this means that we have here these opposing states here of a positive and negative symmetry of the wave functions.
Sorry, can you go through the picture once again? So the x and y axis, this like the charge and the frequency is the frequency of the frequency is the frequency of the resonator, or
the frequency here is just what you probe, your probing frequency. You send here microwaves at different frequencies, so from 6 to, I don't know, 6.2 gigahertz. And the color code is just the amount of signal which you receive from the other side on this point, basically. So here you have a dip in the transmission. This is the resonance dip of the resonator. So if you just look at one cross section here, you just
resonant with what? I mean, you send the pulses on some
Yes.
specific frequency, and you try to match them with
Exactly. Yeah.
with what?
If this signal which is sent here matches the resonance frequency of this resonator,
Of the
this is
resonator.
what we call resonance.
Okay. Yes,
And then
understand.
the signal is basically stored in the resonator, which means that we, at the resonance, we detect less signal at this point, if you have resonance. So basically here we just, well, we detect everything what we sent here, but here we have this Lorentzian dip, the resonance.
So the signal just stuck to the in the resonator. Okay. Okay. Thank you. And sorry, and how do you actually separate? Or how do you know that, like, the left part is actually this anti-symmetrical wave function, and the central part is symmetrical wave function?
How do you know? Good question. Does anybody have an idea how I know?
Okay. So this is just like theoretically we understand that it should be like that. Okay.
Yes.
Okay. Okay.
Yes, of course.
Okay.
Okay, so to operate the quantum bit, as I said, we typically use photons which match this energy transition between the two qubit states, which means that the frequency which is sent should so the photon energy h bar omega should match the qubit frequency perfectly. If we then have this resonant field, the qubit can absorb these photons and also by stimulated emission send them back. At the end, what happens is that the state of the qubit will undergo Rabi oscillation, meaning that as a function of time, from the point where you start to switch on this AC electric field, you will see that the qubit oscillates between the ground state and the excited state.
And you have some kind of dissipation?
Yes.
Just to the external. Okay.
This is one of the topics of this lecture, why actually these oscillations don't persist forever, but they decay. This is exactly due to decoherence.
Okay.
I mean, theoretically, of course, you would just expect these oscillations to be cosonodal forever, but yeah, you will see some reasons in this lecture why this is not the case. But in principle, this resonant driving by Rabi oscillation allows us now to control the qubit state. And you can imagine it's like this. If you start on the ground state of your qubit, you can just start to drive this qubit for a certain time. For example, going from here to there. And you do this with a microwave pulse, which has a certain length, which is just equal to half of the period of these Rabi oscillations. This brings it from 0 to 1, and should you be in 1 and you start to drive, then it just brings it back to the ground state. So this is a sort of odd operation, or pipe pulse. Now the quantum bit can also just be put in a point where it is exactly in the middle between these two states, and so this means that you drive only with half the duration here, and this transforms the ground state actually now into such a superposition of the two qubit states. Here you have just this qubit equally in both zero and ground states. This is called a pi half pulse, actually because you kind of rotate this Bloch vector which describes the qubit state just by pi half. So yeah, you can also use the Bloch sphere as a model to describe the qubit state. Basically, all possible qubit states are here on the surface of this unit sphere here. And if the Bloch vector points to the north pole, you typically say it's in the ground state. Here it's in the excited state. And you can, if you drive it with a half pulse, bring it to a point on the equator here, which are the possible superpositions between the two qubit states. It's not only a single point with such a superposition, simply because you can have two different phases between these two states here. And these correspond then to these different angles here on the equator. Okay, yeah, it also rotates, but not really in the right way. Forget about this. Okay, so another very famous geometry of these transform qubits which we are using is the so-called X-mon. It's still the same system as we have seen before, so we have a capacitor and one or two torsion junctions. Two, of course, is again useful because then with the magnetic flux you can change the resonance frequency of this nonlinear resonator.
So
yeah.
We discussed that there is this parasitic junction.
Yes.
So we will discuss it even later.
Yes.
Okay.
Yeah. Mhm. Okay, yeah, so now this X1 geometry basically means that you just make one of these electrodes in the shape of this cross here. So this is one electrode, and the other electrode, you will just use the ground plane around this cross. So there's a small gap here, so there's no superconductor here, there's superconductor here and there. So again, you form some capacitor between these two electrodes. You have to connect these electrodes of the capacitor with this junction, and if you zoom inside here, you can see this is done in this picture using such a DC grid. So there's two junctions forming a superconducting loop. And again, if you zoom further, you will see again these small counter junctions here. And yeah, of course, then you still have to connect it to a resonator to read out, and you can see how we did it, for example, in Karlsruhe. Here you can see this transform code, this X1. Then here's just this capacitive coupling to the resonator. Here's some transmission line connected to the network analyzer for readout. And now to control the flux inside the DC grid, you can just use a small current carrying wire here, which runs close to this DC grid, so that when you run some current in the neighborhood of this split, it will induce some flux here, so which you can then tune this. The idea why you use this cross actually is explained here. So at the end, for a quantum computer, you need to couple the qubits together. So they need to interact somehow in order to be entangled. And the cross shape is very practically useful simply because such a cross has like 4 different ends. And you could imagine you can then just make a grid of these, two-dimensional grid of these X1 qubits here, where each one has some capacitive coupling to 4 nearest neighbors. And this is a very useful approach, also because it gives a very efficient way to do quantum error correction. So this is also something which I cannot really talk in detail about, but the idea is that you basically have not only a single qubit by which you encode the data, but rather you kind of entangle this data carrying qubit with 2 neighboring qubits, so-called measurement qubits or ancillary qubits. This means that the state of this quantum bit is kind of spread over different qubits. At the end, this allows you to correct for the mistakes, because if you assume that an error, for example, some spontaneous emission of the qubit and some loss of energy affects only one qubit, then we will see that the parity between these qubits will be different. So this will be in 1, 0, and these could be still in 1. And you can then just measure these measurement qubits here and project the state basically to one from which you understand what error did occur, and then you are able to just correct this error subsequently with a pulse that brings you back to your initial state where you wanted to be. Yeah, this approach is actually called the surface code, and it's also the one which has first been demonstrated experimentally in an experiment done by the group of John Martinez in the UCSB in America. And in principle, you can see here, if you have such a set of qubits, the blue ones being the data qubits and the green ones the measurement qubits, then you just, as I said, entangle the state of the data qubit with the neighboring states. You do this with a 2-qubit operation called a C-knot or controlled knot. It just means that you will flip the state of these measurements qubits only if this data qubit is in the excited state. So at the end of this point, you have some entanglement between these state qubits here, and now some error can occur. And by these C-knot gates, actually, this error will spread through the circuit. And at the points where you measure these measurement qubits, you can then see that something must have gone wrong. So we'll see an unexpected result here, and also an unexpected result here. And then later, of course, with the knowledge of these errors, you can again apply these pulses which you need to correct back to the original state that you want to. Yeah, and quantum error correction is of course really important because we can be sure that we will not be able to make a large-scale quantum computer if we don't use this quantum error correction, because there will always be intrinsic decoherence which you need to correct. So coming to the state of the art, These are just some approaches, some pictures from pioneering companies working to realize these large-scale processors. So this is one picture from the Google company, published in 2019 already. They had 53 quantum bits, actually in this X1 configuration, and also there were tunable couplers between two neighboring qubits, for which you actually could use just another qubit which you can tune. You don't really see the processor here because the chip carrying the qubits is this top chip here. And actually this bottom chip here is just the one which you use for control and readout. So this bottom chip here contains the readout resonators and maybe the flux bias lines. And the upper chip contains these crosses, these X1s. And what you do is you just take your bottom chip, the resonators, and you put your qubit chip like face to face, such that these qubits will face the resonator ends, and then you can achieve this capacitive coupling between the two chips. You can also try to scale up in a different way. For example, this is the approach from Rigetti. You could make many small of these, many small chips, maybe each carrying only, I don't know, 8 or 16 quantum bits, and then you can even just connect these chips here with coherent microwave lines between each other, and then try to scale up in this approach. This is also kind of a flip chip processor by IBM. It's actually a multi-layer processor. So you can see here now we have many different layers. One contains the qubits, one contains the readout resonators, and one contains some control lines generating, for example, these local flux biases which you need to tune the qubits. Yeah, and the things have approached very fast. Actually, you can check out IBM's web page where they have actually an overview of their processors which they are currently running. They also offer these quantum processors here for scientists, so you can actually apply to get some processing time, computing time on these processors. For example, if you want to simulate some quantum problem. And the largest processor which IBM has built so far is this 433 qubit processor, which actually is offline at the moment. Yeah, so there was really a big kind of gold rush for the superconducting qubit community in the last years. So many companies jumped into that, and also, of course, funding was very easily flowing. For example, there's a big German initiative trying to build a 9-qubit processor, but using novel qubits and maybe better couplers. Also, KIT is part of this research. And also the European Union actually funded 1 billion euros for 10 years to really try to see how far we can get to this technology. Yeah, these are actually already the biggest players in the field, like at least these are German institutes here, and this here is also the Tarmas University and the ETH in Zurich, for example, and French universities. Yeah, this is a picture of our lab, actually a bit of an outdated one. Well, this is not from our lab, this is from the Google company. I've already shown you that you will need a lot of wires once you want to really control a large-scale quantum processor, because each qubit needs to have some microwave line by which you can do radio isolation and change the qubit state, and also you need to tune the qubit typically with a flux line requiring another set of another wire. And this is now then how you can realize such a quantum algorithm. So the algorithm then basically means the sequences of logic operations, maybe not operations or entangling operations, and all of them are then realized, most of them are realized by resonant microwave pulses. So basically you see here these pi pulses or pi half pulses, either generating superpositions or just making not operations. And at the end you will then just need some signal generator which is able to generate this pulse sequence here, and each qubit then of course has its own pulse sequence which then finally realizes these logic operations. Yeah, so let's now talk about decoherence, the main topic of this lecture. So of course decoherence, we lose somehow the information about the quantum state. And this typically occurs due to some undesired interaction with the environment. So you can imagine that you have the qubit, maybe here represented as some spin here, and then there's some environment. And well, the good idea of Leggett, for example, was to model this decoherence actually by modeling this environment as a bar of harmonic oscillators. Otherwise, it's actually difficult to get some kind of energy loss inside a quantum system because, of course, quantum mechanics is unitary, so the energy should never get lost. But of course, if you have a large number of degrees of freedom, then you can imagine that if this qubit here gives a little bit of energy or couples somehow to different kind of oscillators here, then all this energy will be spread in a large part of actually uncontrolled systems here. And so this means this is how you can actually lose information even in unitary quantum mechanics. So the useful value which you then use to quantify how much decoherence you have. This is typically called the coherence time. And you can understand this the half-life time of the knowledge about the state of the qubit. So there's two mechanisms of decoherence. First is energy relaxation, meaning that you can just, well, the qubit can just emit its energy by going from the excited state back to the ground state under some photon emission. And this means on the Bloch vector, of course, that you get some error in this theta angle here, so you can go from 0 to 1, for example. And the time by which this occurs is called the T1 time. This is a so-called energy relaxation time, or just the half-life time of how long the energy is preserved in your qubit. Experimentally, you will measure this by having the qubit in the ground state, using a pipe pulse to excite it, and then you just wait longer and longer before you measure the qubit. So if you measure directly here, directly after your pipe pulse, after you have put the qubit in the excited state, you will of course find the excited state, but the longer you wait, the more you will find again the ground state. And so this exponential decay, you can just fit to an exponential, and then basically the half-life time tells you about your coherence time.
So, to understand correctly, that this plot is actually like averaged over a big number of qubits?
Of course, yeah. If you, each individual measurement gives you only 0 and 1, of course. You cannot detect the superposition. Our reality does not allow us to directly recognize the superposition. Yeah.
Then, second question, just to make sure. We're still talking about one resonator, and inside this resonator we have one qubit. That's it. We don't have like a big number of qubits which are coupled to the one resonator. No interferences, just one qubit.
Yeah, in principle, yes. But you're right. You could also put couple more qubits to the same resonator.
I mean, in this case, we're not talking about the coherence qubit, right? We're talking just about one single qubit and the relaxation, actually.
Well, we're talking about one single qubit, but of course, the single qubit also will have decoherence.
Okay. But
yeah, I mean, decoherence means the qubit. We lose information about the qubit. That the qubit changes state like spontaneously without our action, without controlling it.
Okay.
And this is what happens here. So you don't do anything in this time here. You just wait longer and longer, and you see the qubit does something. It emits its photon. So the single qubit also, of course, has decoherence. There's a second mechanism how you can lose quantum information, which is called dephasing. And again, if you remember this Bloch vector, Bloch sphere here, if you generate a superposition, you are somewhere on this equator. But it can actually, this angle which defines the point on the equator, this time angle, is also subject to fluctuations. In principle, you can understand this by maybe remembering the real spin in a magnetic field. So you can just take a real spin, some electron, for example, and some magnetic field. And if you do this, then of course you define already the two different basis states. The low energy, like where the spin is aligned with the field, is the 0 state, and this would be the 1 state. And however, if you then are not in one of the ground states, but if you are on the equator, then such a spin, as you probably know, undergoes precession. So it will actually oscillate around this z-axis here at a certain frequency. This is called the Lama frequency. And this lower frequency will depend actually on your strength of this field. It will depend on the difference between the two qubit states. So what is now the problem is that this lower frequency is subject to fluctuations. And this can happen if, for example, this energy difference here is also fluctuating. In a real spin, this typically occurs when you have fluctuations of this magnetic field here, meaning that if you have one spin in one field and the other one in the other spin, then you'll have different lower frequencies, and that's why their phases will typically evolve different speeds, and this means they will dephase from each other. The same actually is also a reason for the dephasing of quantum bits. If you make such a tunable quantum bit, as I told you that you can control the resonance frequency by some magnetic flux. Resonance frequency means, of course, the difference between the energy states here. So again, if you have magnetic flux fluctuations here, then effectively your difference here will fluctuate in time, and this will lead to these fluctuations of the phase of your Bloch vector. So in principle, we also can define some half-life time of how long your system stays phase coherent. To separate from the T1 decay, you then basically call this the T2 time. So the T2 time is called the dephasing time, in contrast to the energy relaxation time called T1. Okay, yeah, this actually was a short and probably too fast introduction to the superconducting quantum bits. Maybe I'll just relax a bit and give you more time to breathe between my sentences. Okay, yeah, so let's now talk about decoherence. Also to answer some of the questions which have already been raised.
Wait.
Sure.
So I'm a little bit confused about the concept of the decoherence of a single qubit. I mean, I understand that if we're talking about coherence, we usually mean that we have like two systems and at least we have some kind of coherence between them. So, for example, in your example, I have a big amount of qubits, and we like drive them coherently, and then like average error. So, still we have this like coherence, so some kind of like, coherent driving or something. So, they are still all of them. They are like connected somehow. And you're talking about like decoherence of single qubit, and I'm a little bit confused. Like decoherence. What is, I don't know, the general thing?
Okay, if you understand decoherence from like a change between two things, then you can maybe just understand that if the qubit stayed in like such a superposition here, yeah? And maybe you can use even like real numbers here, maybe make this easier, then you can just have a phase here.
Yes.
So, in principle, you have also two things here, yeah? Two realizations of reality. Qubit 0 and the qubit 1. And these two realizations can also dephase from each other, basically by generating these fluctuations in the phase. This is one possibility. And again, you lose information about the qubit state if you think you put it here, but then it dephases, then at some point it's here. So, and if you like take the average, the ensemble of measurements, it can be like everywhere after some time. So which then basically means that you have completely lost this information about the phase. Yeah, and the same of course goes for energy relaxation. Here you affect these parameters here. So yeah, for example, this can just grow in time because the qubit needs more and more energy, and of course also this affects a lot of the if you wish coherence between these two qubit states. Okay, so yeah, now let's talk really about decoherence and how we observe them in the lab. So we have already heard that one big reason for this decoherence are material defects, which could, for example, be formed here by these individual atoms in amorphous materials. Last lecture you have seen that this kind of disorder gives room to some of the atoms to tunnel between two states, for example. From here also kind of a qubit, a parasitic qubit, because the atom can be here or there, so also two states, and it's a quantum particle able to tunnel. So at the end, if you look at the evolution of these superconducting quantum bits, shown in this illustration, then you can see that the coherence time, or in this case, the COVT1 time, was not so high in the beginning, maybe only 2 nanoseconds. But then people actually found better and better ways how to avoid this decoherence. For example, I mentioned already this capacitive shunt, which protects from charge noise. And then, in time, by just making better circuits and using better Kubit geometries, people were able to significantly enhance this coherence time. This is actually also called the Moore's law for quantum processors, because like every second year you get a factor of 10 higher coherence time. You also see that this nice evolution here did not persist forever. Rather, since already more than 10 years, we are kind of hitting some kind of hard wall here. So this curve has flattened somewhat, and we are now in this region here. We have a few hundred microseconds coherence time in these qubits, but it has now become very difficult to further improve these coherence times. And yeah, you will see in this lecture that one of the biggest reasons why we have now hit this hard wall are just these microscopic degrees of freedom in the materials from which you make the qubits. So yeah, you've already seen this lower picture in the last lecture. This is the kind of contamination and problems which you can have on certain circuits. So this is a cross section through the electrode. So this is a substrate like silicon or sapphire. This is a thin film electrode, for example, making this cross here. And the electrode will be covered by this amorphous metal oxide. Because it's very difficult, it was nearly impossible to find a metal which doesn't oxidize and form such an amorphous oxide. So you will also have conductive systems in these oxides here. And of course, adsorbates can be there because you expose this to the atmosphere, so anything which hits your sample can just kind of stick there and generate other problems like dangling bonds or dangling hydrogen atoms. Also, residuals are a problem, and maybe trapped mass particles. So now we have one further problem, because now we also have the tungsten tunnel junction. So this kind of sandwich between two aluminum superconductors and some aluminum oxide as a tunnel barrier. And again, we have not really found today a way how we can make this tunnel barrier in a better way. How we can make it, for example, crystalline. So to make sure that we don't have this amorphous structure here, but rather a nice crystalline structure which will not allow these atoms to tunnel. So yeah, we are still using these amorphous tunnel barriers here, meaning that also in the torsion junction we have these tunneling atoms or hydrogen impurities. And here you can have actually more problems. For example, also quasi-particles could be trapped here at the metal insulator interface, forming, for example, again, fluctuating charges. Yeah, this all, of course, will, as you see, generate some kind of decoherence. Short reminder about the two-level system model. So we describe such a tunneling atom, or basically any two-state system which arises from some of these mechanisms by such a double potential. The two states describe the two positions, let's say, of this atom, and we have a tunneling rate between them. And the also important point for this later lecture is that since this potential here is described by the asymmetry energy and the tunnel rate, the transition energy between these two states of the TLS is basically given by this hyperbolic function of tunneling rate and symmetry energy. So if you are in the symmetrical potential with no asymmetry energy, you just the energy difference here is just given by the delta. At this point here, with the symmetric double potential, and otherwise you can increase the transition frequency of the TLS by providing some additional asymmetry energy. And also we have heard in the last lecture that this asymmetry energy can be adjusted or depends on external parameters, which are, for example, the electric field at the position of the defect, by which you can just direct this charge to one side, or by the mechanical strain, which also, of course, affects a lot the local potentials here at this position of the defect by the distance of the neighboring atoms. So just to give you some better understanding how these junctions would look like in reality, This is impressive simulation of junction formation. So these problem of these tunneling atoms in this amorphous tunnel barriers here is important enough so that people actually try to simulate this completely in a computer. So the idea is that you can now just try to simulate this junction formation by a very powerful computer. And this is one of these examples. This is now the oxidation, so there's oxygen present, which oxygen atoms are actually one by one emitted onto the junction. And at some point, another atom should actually just start to come down and be deposited here on this tunnel barrier. And of course, these calculations are rather elaborate, so you need a large computer and much time simply because you have to simulate this here on a picosecond time scale, while of course the complete oxidation can take a few minutes. And you have to then of course to simulate at each time point all the interactions between these atoms. You have to add thermal noise and any other physical effect that you expect to be there. Yeah, and this is then how the junction is formed in a kind of faster version. Here the tunnel barriers now atom by atom just grown, and the oxygen atoms just somehow intermingle here between these two superconducting electrodes here to form this tunnel barrier. And this is really how the junction principle looks. I mean, this thickness of the tunnel barrier is maybe only 20 atoms thick or 2 nanometers thick. So there's really not much oxygen inside, and you see that this is certainly not an amorphous, not a crystalline structure, but some amorphous oxide. So once they actually had the simulation, they could just see whether some atoms actually do tunnel between these two positions, because they can just plot all the positions of all the atoms, and then they were able actually to really see, there is individual atoms tunneling between the positions. So at least this atomic tunneling system model is one valid assumption to form these TLS in our codes. So the first signatures of these tunnel systems in these qubits has been found again in the Martinez group at the UCSB, one of the big pioneers of the field. And one experiment is shown here. So what you again do is you do again spectroscopy. So you try to excite the qubit with the microwave frequency, which you just changed from 8.6 to, let's say, 9.2 gigahertz here. And this is then the population of the qubit, which you can measure after this excitation pulse. So blue means at most frequencies the qubit is just ignorant of this field because it's on resonance, nothing happens. But then at some point you hit the qubit resonance frequency, you excite it, and then in principle you would expect that by changing the bias current or some flux here, you can then also tune this qubit frequency. So we expect some straight line here with a bright color, but what you see is actually not a single line, but you see actually many of these gaps here. So these are now again avoided level crossings, meaning that at certain positions the qubit has to interact with some other quantum systems. So again, you can expect that there's, for example, a defect at this frequency here, and once the qubit approaches the frequency of this defect, it will be kind of repelled, this avoided crossing will appear, and you observe this gap here in the spectrum. You also see that this actually destroys Rabi oscillation. This is a lower picture here. Here it's just at the same basically frequency you try to do Rabi oscillation. So you expect to drive the qubit from the blue state to the ground state, to the excited state, and back to the ground state. So this the time moves in this direction here. So this is actually more or less reasonable Rabi oscillation. But once you are in resonance with such a defect, you will see that these oscillations basically disappear. And of course, this again means that the Rabi oscillation curve is heavily downed. So you could, in the beginning, only observe a few of these oscillations before everything is basically destroyed. So a very important point is that the coupling strength between the qubit and this defects is given by the electric dipole moment of the defect. So basically the charge times the distance by which this atom tunnels times the AC electric field of the qubit mode. So you have some LC resonator, so basically the charge oscillates in the qubit mode always between the inner conductor and the outer conductor and back and forth at the so-called plasma frequency or resonance frequency of the qubit. And this means that there will be an aselectric field across this junction. And since this aselectric field, since the distance here is very small, so only 2 nanometer distance here, you can have actually very strong aselectric fields here inside the tunnel areas. So several kilovolts per meter. And if you now assume you have atomic size dipoles, so maybe 1 electron extra dipole moment, then even such a small dipole moment can generate a large coupling strength. This is, as I said, given by the product of dipole moment times field, and so basically in the junction, those find defects which can have coupling strength up to 15 megahertz. And this is then something which you can easily see in some spectroscopy curve like this, by some very large anti-crossing at certain resonance frequencies. So basically the size of this anti-crossing then is just given by twice this coupling strength G. Then you have now a defect not on the junction but on the surface here, like here on the oxide. Then also you get the same kind of coupling mechanism. Also here will be an aselectric field between the inner and the outer conductor here. But here the distance is much larger, typically about 20 of micrometers or even 100 micrometer. And this means that this field here will be much smaller on the surface. However, you will still see the effect of these now weakly coupled surface TLS, because well, they still couple to this field somehow, and you can typically observe this by measuring now the coherence time, the T1 time of the qubit. So you measure how long the qubit basically stays in the excited state. And if you do this again as a function of frequency, you will see that this decay rate, so the inverse T1 time or the energy relaxation rate here, has at certain frequencies very sharp maxima. So here at this frequency you have much higher relaxation, much smaller T1 time at other frequencies. And again, the mechanism is the same. So you have the qubit in the excited state, you have a defect at some position, you tune the qubit and resonance with the defect, and then they start to exchange this energy, meaning that even if there's no coupled, some energy will be transmitted to the defect, and this means that your qubit will be with a high mobility in the ground state, meaning that you effectively had decay to the ground state. So the coupling strength between the qubit and these defects on the surface is much smaller than those in the junction. You have maybe only 100 kilohertz of coupling strength. However, of course, this will be still very easily visible once you make the qubit coherence time longer and longer. Then even small couplings, small rates of energy loss in these defects will, at the end, break a neck and destroy the qubit state. Yeah, another nice observation on this picture is actually that qubits can also detect single TLS. So you can say that each of these Lorentzian maxima here identifies the resonance frequency of one individual TLS which you have in your system. And moreover, you can even model this or like just fit these Lorentzian resonance curves, and then you get some information about this coupling strength here between qubit and defect, and also about the coherence rate of this TLS. So this is already a powerful method how you can start to learn something about these TLS. So I already mentioned that once you have this qubit in resonance with the TLS, the qubit likes to exchange the energy with this TLS. And this actually goes in both ways, of course. So if you now have the qubit in the excited state, and you bring it in resonance with the TLS, and you see that the qubit state will actually oscillate back to the ground state and to the excited state, back and forth. So this is just this situation which I said. So you have the qubit excited state, resonantly coupled TLS, and the qubit just gives its energy to the ground state and to the TLS and back to the qubit. So these are so-called swap oscillations. And the swap oscillations are pretty nice because this means that you can now use the qubit to actually manipulate the state of this defect. So you could, for example, imagine you have a qubit, bring it to the excited state, you bring it in resonance with this TLS, you just wait for half these swap oscillations before you bring the qubit away again. And then you have actually excited the TLS. Yeah?
So you
At this point, you imply some kind of an estimation for the electric field in the tunnel barrier, or you actually assume that it is precisely, it takes up that value for
Yes.
you.
No, this is a pretty much exactly known value. So the electric field is just depends on the resonance frequency or the energy of this qubit divided by the capacitance. This is just the voltage of the capacitor.
Okay, I get the origin of this. Maybe let me reformulate my question. So this is a macroscopic field that you're, let's say, that I would measure if I were to do some macroscopic experiments, but what about the microscopic field? Given that your material is kind of amorphous, you can totally expect that at different points the electrostatic environment is completely different and this value fluctuates substantially. Is there any understanding of
This is interesting and probably a very subtle point.
So I might just say that this P that you introduce here by this formula is kind of an effective P that takes into account also the local electrostatic environment, right?
Yes.
So in a sense that it encodes not the barrel, let's say, charge times the distance that this charge fluctuates,
Yes,
but also whatever happens around locally.
Yes. Well, this is a good point actually, yeah. You're totally right that the field must not be homogeneous in this tunnel barrier. For example, just by the presence of such a charge. I mean, this charge kind of shields this field at this point below the charge, let's say, yeah. And that's true, yeah. If you have such a situation, typically you will see that, and this is maybe also a reason why these TLS can couple to each other, because they can locally affect their fields by the states in which they are. Yeah, so these sub-oscillations are also useful because they allow you to read out the state of a TLS, and this is just the opposite one. If a TLS is excited, you can use the qubit ground state, plug it in resonance, wait for half these sub-oscillations, and then just measure the qubit. And actually, you don't only get the energy, the population of this TLS, but even the complete quantum state is swapped between TLS and qubit. Okay, so there's different ways now how these TLS now generate problems, how they spoil qubit decoherence. I already showed you that they will pretty much affect the energy relaxation time, depending on how close you are in resonance with the defect. And obviously, when you make these experiments, then each qubit you make will have a different kind of spectrum here, because each qubit will have its own set of randomly arranged atoms, randomly arranged defects. And this is actually the reason why, even if you make qubits identically, they will not have the same T1 time. This is actually shown nicely on these processors. If you take one of these large processors, you have like statistics of the T1 times of a large number of qubits, and it's typically not all at the same T1 time, but there's a large spread. Simply because it's just by chance how close your resonance frequency is in resonance with some of these defects. And this then basically defines the lower end of your energy. Yeah, so this decoherence mechanism of defects, as I said, occurs first by having some electric interaction where the dipole with the defect between the qubit AC electric field and the TLS. And since the TLS as an atom is very strongly coupled to this phonon bath, it will then very quickly dissipate its energy in the phonon bath. And therefore, these TLS here are very nice transducers between like the phonon bath and this superconductor. So even if you make a good qubit and you find a good qubit today, it can also be a not so good qubit tomorrow, because also the T1 time is not constant in time. So these are fluctuations of the T1 time measured on a single qubit without doing anything, just measuring always the T1 time over a course of maybe 60 hours. And again, you get this larger, this rather large spread of measured T1 times. These fluctuations of these T1 times now basically mean that the resonance frequencies of these TLS are also fluctuating. And also lastly, we have seen this kind of picture here, which explains why the frequency of these TLS is not fixed in time, fluctuates, because there can be just another set of TLS defects which have a small excitation energy below the thermal energy kBT. So they will just be able to absorb thermal phonons and be kind of incoherently flipped between the two states, like classical state fluctuators. And if you now have two defects such a thermal fluctuator in close vicinity to a high frequency defect, then they can just interact to each other with like a Doppler moment, for example. So this means that these thermal fluctuations of this low energy defect can change then the energy, the resonance frequency of this high frequency defect by changing the symmetry energy. Yeah, this then of course gives rise to these temporal fluctuations here, just again depending how many thermal fluctuators you have in the vicinity of this TLS. Yeah, and you see also that this already indicates that when the TLS comes closer to the qubit, the diameter of the qubit will of course be decreased. And likewise also there will be some shift in the qubit frequency. By this again Voidal repulsion, and sometimes you can even see that your qubit frequency then shows these kind of telegraphic fluctuations between two values as a function of time, which now basically mean that you can use the qubit directly to monitor the state of this thermal fluctuator by going over this TLS here, which is affecting the qubit resonance frequency. Yeah, last lecture we also heard the comment that vibrations of the pulse tube, which you use to cool the cryostat, can actually generate problems. And here's an example. In the modern cryostats, you use these pulse tube coolers, which always work similar to stirring coolers. So you change the pressure in the helium gas regularly, like once per minute. And this, of course, generates vibrations in your cryostat. These vibrations are shown here. This is the acceleration measured in such a cryostat. When you have this pulse tube, this is this yellow curve. If you switch a pulse tube off, you basically get a very silent situation here. And if you now measure at the same time, like you measure this acceleration, the qubit population, you can see that actually there's kind of synchronous parasitic population in the qubit. So whenever the pulse tube is on, you get these peaks here where the qubit is in the excited state while it should be in the ground state, and you get much less of these problems when the pulse tube is off. And yeah, the same authors actually also check whether we can just excite the qubit by hammering on the cryostat to generate these vibrations like artificially. And they did this here with this electromagnet, which you could just pulse so that a small hammer here hammers here on the top of the cryostat. And again, you can measure that this generates some acceleration, some vibrations in this cryostat. And if you measure at the same time the qubit state, you see that after this pulse, the qubit has a higher probability to be excited, and then again decays back to its ground state within its demand time. Yeah, and so it's not yet clear where these coupling to the vibrations come from, but if you ask me, I'm pretty sure that this must be TLS, because those are the only things which are small enough atomic size such that they can actually be significantly affected by these formats. So actually in Karlsruhe we made a series of experiments where we now exploited this coupling of the TLS to the mechanical strain. And the principal idea is that we wanted to be able to tune these TLS. So as I said, we can use electric field or mechanical strain now to change the resonance frequency of such a defect along such a hyperbola. And our approach was rather simple. We just used the qubit chip here and installed it in some kind of metallic frame. And on the bottom of this chip, we put a piezo actuator, which you know is a crystal, which you can change the length just by putting some voltage. So if you put the voltage on the piezo, you basically just bend the qubit chip a little bit, so you deform it a little bit. And also we could apply a piezoelectric field simply by putting some DC electrode in the vicinity of this qubit, maybe one electron above, maybe one electron below, again connected to a voltage source, and then you have basically some DC electric field which you expose everything here on the surface to this electric field. Yeah, this was our approach, how we realized this. This is now the picture of the qubit chip. So there's microwave transmission lines, which you can see here. They are connected here to on-chip coplanar waveguides using some bonding wires, which you cannot see here. And then on the other side of this chip, we have a small hole in the bottom of the sample holder, which then is just exposed to this piezo, which is installed in this copper part here. So we press basically on the center of this qubit chip here from the bottom. and they were able to control the mechanical strain. The DC electrodes, which we need to apply to the electric field, is just some copper foil which we glue on the lid of the sample housing here. So again, this is connected to a voltage source here and should expose everything to some DC electric field. And at the end, you just close this cover, so then the electrode here will just float maybe 1 millimeter above this fluid. So to test whether this actually works, we can then again use this measurement here. So again, this is the qubit loss rate, the inverse T1 time, measured as a function of qubit frequency. Showing again these maxima here, where I told you each of these maxima is now the resonance of one TLS. So if this is true, we should be able to change the position, the frequency of these peaks here, so we were applying some mechanical strain, applying some fixed voltage here. Yeah, and this is the result. So this is basically the same measurement like this. So the vertical axis is again the frequency here. The color scale now is this, indicates the T1 time of the qubit. So dark pixels mean we have a short T1 time. And of course, we will then, for one cross-section, just see some points where we have this maxima here, these dark pixels. But now, if you change the mechanical strain by putting some voltage on the piezo, you can see that these dark pixels really nicely arrange on these hyperbolas here. So this is actually a very nice proof that, in fact, we are able to tune these TLS by the mechanical strain, and also that the underlying standard tunneling model seems to be correct because you can only observe hyperbolas here where we apply this mechanical strain. And this is actually really a nice experiment because it provides many insights into what actually goes on into your tunnel barriers on your surface. So what kind of defects you have there and how will you have. This is a wider picture. Again, changing the mechanical strain and detecting the qubit T1 times a function of qubit frequency. Yeah, and you can really see this large plethora of different hyperbolas. You can also see more or less the straight lines here, but this just means that this tunneling energy of this defect is very small, so basically you just see this kind of linear edge here of this hyperbola. Yeah, and of course, I said this is a very useful measurement. You can just, for example, count the number of hyperbolas which you have here in a given frequency range. This gives you an idea how many, what about the TLS density in your tunnel barrier, for example. And you can also observe many other interesting effects. So, for example, if you look closely, there are some non-hyperbolic traces. This one, for example, here is not really a hyperbola, but rather something which also has some more local crossings here and there. And this is actually kind of a textbook signature of two coherently coupled TLS. So you can imagine in a tunnel barrier you have two TLS close to each other, so they can couple to each other via dark reliable coupling or via strain coupling. And now when we change the mechanical strain, what we do here is actually that we don't really change so much the frequency of this TLS, because this may just be weakly coupled to the strain. But there can be a second TLS, which we do tune by the strain. So this means we can tune one TLS to resonance with the other TLS. So we would have resonance here and there. And if they are coupled, then we will expect, of course, to see a wide level crossing at these points, which now is just what we see here. So you can imagine that another TLS is tuned through this signature like this, generating a level crossing here, goes down, comes up again, and again crosses the qubit, the other TLS here. Then the reason why actually the frequency of this high frequency here has this kind of step is also well understood. What you do is, when you tune this TLS2 through the symmetry point, you basically change the position of the ground state. So here you have the ground in the left lobe, here you have it in the right lobe. So basically, this means that when you change TLS2 ground state, TLS1 will respond with the change of its energy. And this is just what is known as longitudinal coupling. So the state of one TLS changes the frequency of the other TLS. And in addition comes, of course, the exchange coupling here, the resonance coupling, where both TLS have the same energy, and you get these avoided local crossings. Yeah, this was actually the first experiment where we could really prove or see directly how these defects interact. And of course, then you can start to completely analyze this system, for example, by looking at the interaction Hamiltonian, now containing both this longitudinal coupling and this transversal coupling here. And yeah, since we have this very nice method to monitor these recent resonance frequencies, you could completely characterize these coupled field systems. Another thing where you can see the interactions between defects are these. This signature here. The resonance frequency of this defect is obviously not constant, it just fluctuates between two positions. Two resonance frequencies. Kind of a telegraphic fashion. Yeah, this is just again this picture of interaction. You observe here this high frequency defect in a range where the qubit can be accessed. You can access it with a qubit and observe resonance. And this must be coupled to some thermal TLS, which you cannot directly measure because you cannot tune the qubit to below the thermal energy. But you can still see that the state of this fluctuating thermal fluctuator is now nicely visible by just its tuning effect on this high frequency defect, which is then measured with the qubit. Yeah, and this, of course, is an also very powerful technique to study interactions between these defects and also get some idea about the density of the thermal fluctuators which you have, which again would not be accessible otherwise to measure. Okay, so I guess I had produced enough words for today. And I guess we can stop at this point and then continue in the next lecture with more fancy experiments, what you can do with qubits and how you can further study these defects. And also we will see, hopefully, how we can find ways to mitigate these problems, so how to avoid all this decoherence by these defects, maybe by finding better materials, trying to reduce the density of these defects. So with that, I would like to thank you very much for your attention. I hope I was not talking too fast. I was probably talking too fast, but well, I'll try maybe next time to relax a little bit myself. And maybe we can use the last 5 minutes for questions if you have any.
You explained how to study TLS by means of qubit spectroscopy. Is it possible to use this knowledge, this study of microscopic nature of TLS, in order to predict the decoherence rates of a qubit due to TLS and how it relates to actual measurements?
Yes, this is a very good question, yeah. And I tried for a long time. In principle, you're totally right. We can directly see what kind of defects we have here. We can even measure the coherence time of these defects and the coupling strength of the qubit. So in principle, we should know everything to predict the T1 time of the qubit. This is correct. If I try this and, for example, just use these, I don't know, 40 TLS in this window here, which I can see, and then I use them to calculate the T1 time of the qubit, then I don't get the T1 time of the qubit. So these defects which you see here cannot be the only responsible ones which limit the coherence time.
You at least get something smaller or bigger than the fact.
Well, I get the qubit is less coherent than I would expect from the number of defects which I find here. So there is either other mechanism which we don't yet have on our calculation, which we don't understand yet, but actually maybe also a reasonable assumption is that what we see here in the spectroscopy is only the strongest coupled defects, the ones which really are so strongly coupled that they significantly reduce the energy relaxation time during the T1 time of the qubit. There could be a large number of more weakly coupled defects, which would not generate by themselves these individual resonances, but in the sum as an ensemble, they would still possibly generate this required decoherence to explain the observed coherence times of the qubit. Yeah.
So by this measurement, you can probe the frequency of those defects as a function of external parameters. Is there any way to extract, let's say, the line width of those resonances?
Absolutely, yeah. So you can just fit each of these cross sections here in these measurements. Like you can just make a Lorentzian fit to these curves here.
And those will be the resonance of the TLSs themselves.
This will be the resonance of the TLS, and also this formula for these Lorentzians here. This contains the coherence time of the TLS. So the coupling strength to the TLS between qubit and also the coherence time of the TLS.
So it looks like there's an independent way to discriminate between the coupling and the line width.
It's not straightforward to distinguish here because you have a product here, of course, of both, so you can maybe get some reasonable assumption for the product of these two numbers.
let me explain why I'm asking, because it seems like if you can somehow indirectly assess the line width of the TLSs, then you can compare the path that they see with the path that the qubit sees, and see if they are somehow correspondent.
Very nice, yeah, very good idea, and we have a measurement in the next lecture just showing this. That you can now actually use the TLS as kind of a sensor for the modes in its own environment. By just seeing how the T1 time of this TLS actually depends, for example, on the strain, on this frequency, then we can actually probe the phonon spectrum, each individual defect will see.
Could you show this plot with TLS?
The cover TLS?
So,
oh, this
yes. As I see, your maximum T1 is like 100 nanoseconds.
Yes.
Yeah, so if we go to the upper time scales, we expect that the density of your TLS will be small. Yeah, and as the told us in the first lecture, it's quite nice to have an ability to move the frequency of your qubits to perform gates. If you have a large system of qubits, you want to decouple them. Due to the decoupling, your qubit goes through a lot of TLS.
Exactly, yeah.
What happens in this model?
This is exactly one problem. When you have a TLS and you tune your qubit through it, then you get some kind of Landau-Zener transition, right? So there's some interaction while you do this, while you tune through, and then some part of the energy or quantum state can be swapped, and it depends basically how fast you tune it through, how much your qubits are going to be affected. This actually occurs, and in fact it's a problem for the readout. It limits the readout fidelity of these qubits. Because typically, especially these qubits, to read out, you tune the qubit quickly to low energy, which actually tunnels for this phase qubit, which is shown here, and then you lose this energy, this state information by just this time-dependent Landau-Zener interactions with these defects. Actually, you can also see Landau-Zener interactions in this picture. Actually, maybe better this picture. So this measurement was done by exciting the qubit to the ground state and then tuning it to these frequencies, different frequencies. Then we just stayed there for some time to see how the runtime develops, and then we tuned back and measured the qubit state. And actually, the qubit was started at this frequency, and you see that you basically tune the qubit here to this strongly coupled TLS. And then you wait for some time and you tune again through it. And then actually these oscillations here, these are actually Landau-Zener Stückelberg, if you wish, oscillations and probabilities. Because you have like, you tune the qubit through the thing, you have some kind of half transition, let's say, you have then a phase evolution between the two states, and then depending on the time you wait there, the phase will evolve, and then you come back a second time, and then it depends actually whether you get now further oscillation in this one direction or the other direction, depending on the phase. And this actually turns out at these oscillations here.
Did you try to measure the distance as a function of the Dragon power?
I'm sorry?
Did you try to measure the distance as a function of the Dragon power?
It's a function of detecting power.
Dragon power. Because the area measure is to one such a frequency for Dragon power.
So to make these kinds of experiments, I need to have the qubit propelled in the silent state. Because then I have like the maximum contrast to behave back to the ground state. So I only applied pipe pulses here. But maybe you mean that I could make the pipe pulses a higher angle. Well, if it's a pipe pulse, still the single photon should only end up in the qubit. So there is no kind of way how to use this direct how to separate the T or to excite the TLS directly. If this was your idea.
Yeah. But let's see if you drive halfway with just a set of kills, then you will see energy.
Yeah, interesting, you're right. You could just shoot like a very strong pulse or material or tunnel barrier which excites all the TLS, or saturates them. And then, in fact, the qubit should not be able to absorb any more energy. Which is probably not true. I mean, you will not get any more energy relaxation, energy loss, because then you get the same kind of energy back as you put in the TLS, but still the phase won't play a role. It's actually anyway not easy to separate such a TLS of, for example, this tunnel barrier. It's not easy because the TLS itself has some, well, atomic size data moment. You would need a very high amplitude to actually couple strongly enough to this TLS to excite it directly. But nevertheless, the next lecture also you will see some experiment where I kind of put this experiment nevertheless. There's a way how it works in fact. So how I can actually populate the TLS state and then basically use the code to see how much the excluded population has in the past.
Thanks.